In continuity of our discussion on the ideas of quantum mechanics, this is the introductory nuclear physics, and I am Dr. Nasir. Um, Today we will sum up our discussion on the application of quantum mechanics towards the hydrogen atom and see its implications. So let me recap the what we have discussed earlier about the quantum states of electron in hydrogen atom. We have concluded that there are three principal quantum numbers that come through the solution of Schrödinger wave equation, and these are principal quantum number n, angular quantum number L, magnetic quantum number ML. N is discretized and its value can change from 1, 2, 3, and so on. It cannot have value of 0 because n is equal to 0 gives a trivial solution, and it's no solution. The angular quantum number starts with L is equal to 0, and it stops before n minus 1. So its upper value is n minus 1. The magnetic quantum number is ML, and its value is between 0, plus minus 1, plus minus 2, and till plus minus L. So from minus L to 0 and from 0 to plus L, it can vary. The magnetic quantum number is responsible for telling us that the angular momentum vector has a direction, and its direction is specified through this quantum number, and therefore the where it is oriented in the space is fixed, and it cannot have any orientation in the space. Only few discretized orientations are allowed, so this is termed as space quantization. We have already seen that if we want to write down the possible total signature or the address of the electron, say for n is equal to 1, the ground state, then L is less than 1, so it is 0, and ML can have only value 0. So the complete set for the ground state is 1, 0, 0. The first excited state that we see is possible only with n is equal to 2. And for n is equal to 2, there are two choices, L is equal to 0 and L is equal to 1. And L is equal to 0 means again that ML will be 0. And for L is equal to 1, there are possibilities that ML can have value 0, and it can have a value of minus 1, and it can have a value of plus 1. Therefore, there are three possibilities for L is equal to 1, 0, and plus minus 1. So the possible states for the system, the ground state like situation, if the first excited state is 2, 0, and 0, and then 2, 1, 0, and then 2, 1, and plus minus 1 due to the ML, the orientation. The two orientations are possible. The energy levels for the electron. From the quantum analysis, we come to know that the energy is basically discretized, and the ground state is the lowest possible state. And if we can convert the ground state value into the energy units, the electron volt energy units, then the ground state value is minus 13.6 electron volt for the electron in hydrogen atom. 1 electron volt is basically expressible in terms of joules, and it is 1.6 into 10 to the power minus 19 joules, a very, very small value. So we see this, that the lowest possible state, the nearest state that electron can occupy closer to the nucleus is the 1s. Now, S we know is for L is equal to 0, the angular quantum number, and for S is equal to 0, there are possibilities 2s, 3s, 4s. Similarly, for P, 2p, 3p, 4p. For 1p is not possible because L must be less than the value of the principal quantum number n, and here n is equal to 1, therefore it cannot be there. P starts from 2, and D starts from 3 and 4, and F starts from 4. Now, in this example, you can see that the transition from 3s to 2s is not possible. You don't see any arrow showing a direction that from electron in this state will fall down to 1s and become closer to the nucleus. This kind of transition is not allowed. It is due to the selection rule. The first selection rule is delta L must be plus minus 1, either plus 1 or minus 1. So here from S to S, L transition remains, so delta L is 0. However, from P to S, this is one jump. Similarly, from P to D or from D to P, transition is possible. From F to D is possible. From F to P is not possible. Similarly, delta M must be either 0 or plus minus 1, and this is the orientation, the direction of the vector for the angular momentum, capital L. The L vector must have the direction change, either 0 change or a plus 1 change or minus 1 change. Now we see here one example of a possible transitions, and we can see the expressions here are shown only for L is equal to 0, L is equal to 1, L is equal to 2, and the nomenclature is S state for L is equal to 0, for L is equal to 1 P state, and L is equal to 2 D state. So you don't see any D state transition which is going to S, because it is with the delta L change of 2, and it is not allowed under the transition rules. So selection rules forbid this kind of transition. Therefore, they are not shown and they are not possible. Another thing point out is to be pointed out here is that the ground state energy, if you divide this energy with the n square, the n is the level. This is the 1s, and then this is 2s. So n is 1 here, 2 here, 3 here, 4 here, and for this, if you divide 13.6 divided by 4, the 2 square, you get 3.4. Similarly, if you divide this by 9, you get this. If you divide by 16, you will get this. So you can see that the gap between these two is large, and the gap between these two states, between 2 and 3, is small as compared to the first gap. Now let me talk about the electron spin. Electron spin is basically the intrinsic angular momentum. So every electron showing an intrinsic angular momentum, and it is spin, and its magnitude is same for all electrons, and people have shown it now through various experiments that this is true, and the effect is called Zeeman effect. The quantity small s is basically the spin angular momentum's quantum number. So this quantum number s for the spin angular momentum is describing the spin angular momentum. The value of s tells us the value of capital S, and it is in terms of h cut, where h cut is again, as you know, h divided by 2 pi. Now, this s can have only possible choices like half. The spin magnitude quantum number is given by ms, and its value is plus minus s, that is plus minus half. Either the spin will be half plus or with the minus. So therefore, if we now write down all the possible quantum numbers that are coming out of the quantum theory, they are the principal quantum number, n, the orbital quantum number, L, the magnetic quantum number, which is telling the direction, is ml. The spin quantum number is ms. Now, the quantities that are associated with these, the principal quantum number has the energy relationship. The orbital quantum number, small l, is related to angular momentum magnitude, the capital L. And the magnetic quantum number, ml, is related to the direction of the angular momentum, and it can vary from minus L to plus L, as 0 is included. The spin quantum number can have only 2 possible choices, minus half or plus half, and it shows the direction of the spin, and it is the magnitude, and it tells us about the spin angular momentum as well. Now, the effect of the electron spin on further things is that now we have the quantization of the spin, and the spin quantum number ms has possible 2 choices. Therefore, the complete set, which is going to describe the hydrogen atom's electron, is given by n, l, ml, ms. So, for example, if we are discussing the possible ground state that was previously available to us as 1, 0, 0, now due to the spin and the presence of the spin, we come to know that this is not really one state. It is basically the 2 states, 1, 0, 0 plus half, and possibly 1, 0, 0 minus half. So this is complete address of a 1 electron with a spin up, and the 1, 0, 0 minus half is the possible address of the second electron, which has a spin down. Now, let us, using this complete idea of the quantization, try to write down the spectroscopic notations. The ground state we come to know that its degeneracy is 2. So let's see. The first excited state for n is equal to 2. N is equal to 2 is the excited state. So how many possibilities are there? If we completely write, we see there are 8 possibilities plus half the ground state and minus half with the ground, the L is equal to 0 value. L is equal to 0 value, then L is equal to 1 has these possibilities. L is equal to 1 has these other possibilities, and we see that these L is equal to 1, 3 possibilities, and L is equal to 1, 3 other possibilities with variation with the minus half and the plus half. So remember the spectroscopic notation for L is equal to 0 is S, for L is equal to 1 is P, and so on. And the selection rule requires that delta L must be plus minus 1, and the delta ML must remain 0 or plus minus 1. So the idea of shells and sub-shells of electrons can be further discussed. When the spin was there and it was discovered, and people came to know about the electron spin, then Pauli wrote down the exclusion principle. We see that many electron atom, a electron which contains many electrons, is a stable atom when the total energy is minimal. Its total energy is minimal. Only one electron can exist in a particular quantum state in an atom. And by particular quantum state, the meaning of the quantum state is the 4 quantum numbers, the exact address. So the atomic shells got their names from the energy, the total energy. For n is equal to 1, the ground state is K shell. The first excited state is L. The second excited state is M. Then is N and O. So this is usual practice in chemistry and physics, that atomic shells are expressed in terms of N. N is basically related to the total energy. Now we talk about the subshells. The electron that shares a certain value of L in a shell are in the same subshell. So let's see what we mean by this. For example, if we talk about the sodium's electronic configuration, we write it in the following manner. Let us see. 1s, and as you know, s means L is equal to 0. The small l equal to 0. The angular quantum number, and for that we see that there are 2 possibilities, spin up and spin down, and therefore S will have at the most 2 electrons. Similarly, 2s is going to have the 2 electrons. However, P, as we have seen previously, the P has a possibility with the help of L is equal to 1, that we see that 2L plus 1 possible states are possible. So there are 3 states possible, but spin up and spin down make it 6. So 6 electrons are possibly occupied. So 1s, 2s, and 2p in total have 10 electrons. Now the 11th electron is in the 3s state, and another choice is available for the s, either up or the down electron is there. So it means that we have covered the 1s, n is equal to 1, L is equal to 0, 2s subshells, that are containing 2 electrons. And 2p electron configuration will have 6 electrons, and 3s will have 1 electron, and total will be the 11 electrons for the sodium. Now we come to see and look into the capacities of the shells and the subshells. So there are possibly 2L plus 1 different values of ML. And for any value of L, these are the total possibilities. And the spin magnetic quantum number can have 2 possible choices, plus half or minus half, the spin up or spin down. So each subshell will have 2L plus 1 possibilities multiplied by the 2. The 2 stands for the spin up and spin down 2 possibilities. So this is the total number of electrons that will be occupied in the subshell. For example, L is equal to 0 will have 2. L is equal to 1 is going to have 3 multiplied by 2, which is equal to 6. For L is equal to 2, it will be 2 multiplied by 2, 4, plus 1, 5 multiplied by 2 is 10. So the maximum number of electrons in a shell are then 2n square. The subshell is the shell is the name of the divisions due to the L splitting and the further splitting due to the possible choices of the spin quantum number, and the total is n square. So if we see the closed K shell, it will have 2 electrons. A closed N is equal to 2, which is L shell, will have 2n square, which is 8. So we'll have the total 8 electrons. And a closed M shell, that is n is equal to 3, will have 3 squared, 9 into 2, 18 electrons, and so on. So if we want to see the distribution of electrons by the energy levels and in the subshells, then we can see that they are distributed according to the energy levels, the first, second, the third, and so on, and 1s, 2s, 2p, 3s, and 3p. The 3s has a lower value of energy as compared to 3p, and we can see here the 2 electrons, 2 electrons, 6 electrons, 2 electrons, 6 electrons. So we can also tell that the 1 n is equal to 1, the energy level, the ground state will have maximum 2 electrons. The first excited state will have 8 electrons at the most, and 18 electrons are there for n is equal to 3, and for n is equal to 4, the third excited state will have 32 electrons. And we can write down the distribution in terms of the 4s, 4p, 4d, and 4f. So this is how the subshell capacity is filled, and we must remember that the Pauli exclusion principle is obeyed, and any transition which is going to take place will obey the selection rule. We stop here with the summing up of the capacity, and we would like to show you with the different colors. The S shell has 2 electrons in general, and the P has 3 possibilities due to L, but then due to the spin, it becomes 6. As you can see, the last for the sodium, these are the 2 electrons filled here, then 2 electrons and the 2 electron, the spin up and the spin down. In this figure, the spin up is shown with this arrow, and spin down is shown with the arrow pointing towards the ground. And the filling mechanism is also written in this form, that the 1s and the first term stands for n, the principal quantum number, and then comes the s, which is L. L is equal to 0, and the 2 superscript tells us the total number of possible electrons that can be filled in this. Similarly to S2, and then to P6. The P is L is equal to 1, and 2 is N, the principal quantum number. And that's how the whole story of the electron distribution is written for the multi-electron systems. And the quantum theory is really very powerful tool in telling us the orbital diagrams, the total electrons, and the electron configuration for any element, and its a specification is really quite an elaborate. If I wish to look at the shape of the orbitals, then S orbitals are basically the spheres, spherically distributed. So the S1s is a sphere with a smaller dia, and it is close to the center or the nucleus. The 2s is a bit far away, and it's a larger sphere as compared to the 1s sphere. Similarly, 3s sphere is even larger as compared to the 2s. If we try to plot all these three together and would like to show you with the sheets that what is inside, the deep inside is the S1s, the outer is the 2s, and then still larger sized is the 3s, and all the spheres are telling about the orbitals where the electrons are, the probability of finding electrons for those energies is maximum. And that's the place where the waves, the electron waves, are really the stationary waves. Similarly, p orbitals are here, and along the x-axis, this is the 2px, and it is a cross-sectional view which is shown here. If I try to assimilate it, it is actually a donut-shaped distributed thing. Similarly, 2py, similarly 2pz, the y directional this orientation, and z directional. And if we combine all these together, we get the distributions along the x-axis, the y-axis, and z-axis all together, summing this, that the probability of finding electron is maximum in these regions for these energies and the angular momentum. So the electron waves and their distribution functions, or the wave functions, are really very, very different. What we had in mind when we were thinking in terms of particles. No more particles. These are the stationary waves, and the stationary waves have their probabilities, and the probability of finding these waves becomes a maximum somewhere, and it becomes a zero somewhere. And the distribution function is the orbital. The electron configuration, if I sum completely, here is the idea that the 1s is at the lowest, the ground state for n is equal to 1. Similarly, n is equal to 2, and then n is equal to 3, and n is equal to 4, and so on. However, we can see that I have shown here a greenish region in which I want to stress that the S level can only be filled with the 2 electrons, the spin up and spin down. any of the S shell will be filled like that. And the P shell has all three possibilities. So it's not just 3 electrons. There are total 6 possibilities, 3 multiplied by 2, 3 multiplied by 2, and so on. So we have larger occupancy for the P and D shells, and the smaller occupancies for S shells. However, as we go up, the energies, they keep on changing. The lowest ground state energy is the negative energy, and it is a large negative energy, and as you go up, it becomes eventually 0. And the distance keeps on changing. However, this energy for 4s is lower as compared to the 3d. So therefore, 3d is not as in the vicinity of 3p. The 4s comes first. And that's what the electron configuration is all about. And it tells us how the electron are going to be filled in a multi electron atom, and how the energy distribution will look like, and how the transitions will take place. From P to S, the transition is going to take place, and from P to S, transition is going to take place, and from D to the closer one is, but the transition will take place because of the L. It is going to take place between these two, the D and the P. Here we stop. We have learned a bit about the electron configuration, and the conclusion is that the quantum theory, which is based on the Schrödinger wave equation and the wave function, and the wave function squared is the probability of finding the particle or the wave. And from that, we have seen that there are 4 quantum numbers that are responsible, and we see the energy shells, and then sub-shells, and the electron configuration or the distribution within the atom. We have figured out, and we now know that this is really well suited, and it obeys the experimental spectroscopy as well, and it has been tested through the other experiments, and the behaviors are very well suited. So quantum mechanics, and it's a shell-like model, is really very, very fine. The extension of this model has been done to the nuclear part, the nucleus itself, and in coming lectures, I'm going to use that idea that the nucleus is also behaving like just like the atom, and the electrons orbiting around the nucleus, and we can use similar quantum mechanics for the nucleus to write down the configuration for the protons and configuration for the neutrons. So we stop here. Thank you so much.